A vision language model looks at a picture and answers questions about it in plain language. But images and words are completely different kinds of data. The trick is to turn both into the same thing, list of numbers, and reason over them together. Start with a picture. The encoder doesn't see a dog, it sees pixels. So first, it slices the image into a grid of small patches, the way you might cut a photo into tiles. Each patch is then turned into a vector, a short list of numbers that captures what's in that tile. Do this for every patch, and the whole image becomes a sequence of vectors. That's the key idea. An image rewritten as a sequence exactly like a sentence in a sequence of words. The question gets the same treatment. A tokenizer splits it into tokens, and each token becomes its own vector. So now the image and the text are both sequence of vectors, the same kind of object, just coming from different places. And here is the catch. Visual vectors and text vectors have the same shape, but they were learned separately. The same idea can land in different places, so the model can't yet tell that the green tile and the word grass mean the same thing. Imagine an embedding space, a map where similar meanings sit close together. The vision encoder built one map and the language model built another. On those two maps, the picture of a ball and the word ball land far apart. They simply don't line up yet. This is the projector's job, often just a single linear layer. Trained on millions of image and text pairs, it moves the visual vectors onto the language model's map. Each image point slides across until it sits beside its matching word. The picture of a ball right now next to the word ball. Vision and language finally share one space. With everything on the same map, we simply stitch the two sequences together, the image vectors first and the text vectors, into one long input. To the language model, it now looks like a single, slightly unusual sentence. As the model reads this combined sequence, attention lets every token look at every other one. When it focuses on the words playing with, it reaches back to the patches that matter, the ball. That link from a word to the right region of the image is how the model grounds language in what it actually sees. The model writes its answer autoregressively, one token at a time. It emits a token, appends it to the input, and reads the whole sequence again to choose the next one. Because the image is always part of that input, every step can recheck the picture. Finally, those generated tokens are decoded back into words. The dog is playing with a red ball. The model didn't recall a stored caption. It built the sequence piece by piece from what it saw and what was asked. So that's the whole idea in one line. Turn pixels and words into vectors, pull them into one shared space, then let attention reason over all of it. That single trick is what lets these models caption images, answer questions, read documents, and reason about almost anything they can see. Thank you.